Module 4, Unit 7. Transportation, Assignment, and Network Models. Transportation, assignment, and network models are essential in operations research and management science. These models help optimize the allocation of resources, minimize costs, and improve efficiency in various logistical and operational tasks. The transportation problem involves determining the most cost-effective way to transport goods from multiple sources to multiple destinations while meeting supply and demand constraints. In a typical transportation problem with 4 sources and 5 destinations, the linear programming model will have 20 variables, each representing the quantity transported from a specific source to a specific destination, and 9 constraints, 4 supply constraints and 5 demand constraints. The objective is to minimize the total transportation cost while satisfying all supply and demand requirements. The transshipment problem extends the transportation problem by allowing intermediate nodes where goods can be temporarily stored or transferred before reaching their final destination. This model is particularly useful in complex supply chains where goods may pass through distribution centers or warehouses. The formulation involves defining decision variables for each segment of the transportation route and setting up constraints to ensure that the flow of goods through each node is balanced. Solving this model helps optimize the entire supply chain, reducing costs and improving efficiency. The assignment problem focuses on assigning tasks, jobs, or resources to agents, machines, or locations in the most efficient way. A common example is assigning employees to tasks or jobs to minimize total cost or maximize efficiency. The formulation involves defining decision variables that indicate whether a specific task is assigned to a specific agent. The constraints ensure that each task is assigned to exactly one agent and vice versa. Solving this problem typically involves using the Hungarian algorithm or linear programming to find the optimal assignment that minimizes total cost or maximizes efficiency. The maximal flow problem seeks to determine the maximum flow of goods or information through a network from a source node to a sink node. This problem is crucial in various applications, such as optimizing traffic flow in transportation networks or maximizing data flow in communication networks. The formulation involves defining decision variables for the flow on each arc of the network and setting up constraints to ensure that the flow into each node equals the flow out of each node, except for the source and sink nodes. The objective is to maximize the total flow from the source to the sink. Algorithms such as the Ford-Fulkerson method or linear programming can solve this problem efficiently. The shortest route problem aims to find the shortest path between 2 nodes in a network. This problem is widely used in logistics, transportation, and communication networks to minimize travel time or distance. The formulation involves defining decision variables that indicate whether a specific arc is included in the path and setting up constraints to ensure that the path is continuous and connects the source and destination nodes. The objective is to minimize the total distance or travel time. Algorithms such as Dijkstra's algorithm or linear programming can solve this problem effectively. The minimal spanning tree problem focuses on connecting all nodes in a network while minimizing the total distance or cost. This problem is common in designing efficient network infrastructures, such as telecommunications or transportation networks. The formulation involves defining decision variables that indicate whether a specific arc is included in the spanning tree and setting up constraints to ensure that the spanning tree is connected and includes all nodes without forming cycles. Algorithms such as Kruskal's or Prim's algorithm are typically used to solve this problem efficiently. In a facility location problem, a company might consider opening a new production facility at one of several potential locations. For example, if a company is considering opening one new production facility and 3 locations are being considered, 3 transportation models must be developed and solved, each representing the transportation costs and constraints for a different potential location. By comparing the results, the company can determine the optimal location that minimizes transportation costs and meets demand requirements. In a typical shortest route model, the objective is to minimize the time or distance to get from one point to another. For instance, a city planning for the Grand Prix might use this model to evaluate its transportation system and determine the necessary expansions to handle the large number of visitors. The model helps city planners identify the shortest route and optimize traffic flow, ensuring that the transportation system can efficiently accommodate the increased demand. The maximal flow model can help determine the capacity of a transportation system by evaluating the maximum flow of goods or passengers through the network. This model is particularly useful for city planners who need to assess the current capacity and identify potential bottlenecks in the transportation system. By solving the maximal flow model, planners can determine the necessary expansions or improvements to ensure that the system can handle the expected increase in traffic during the Grand Prix. The minimal spanning tree model is used to determine how to connect all points of a network while minimizing the total distance between them. This model is useful for designing efficient network infrastructures, such as telecommunications or transportation networks. For example, a company might use this model to connect security video cameras to the main control site from multiple potential trouble locations. By finding the minimum distance route for the conduit, the company can minimize the installation cost while ensuring that all locations are connected. Unit 8. Waiting lines and queuing theory. Waiting lines and queuing theory are critical components of operations management, helping businesses analyze and optimize their service systems. One of the fundamental concepts in queuing theory is the trade-off between the cost of waiting time and the cost of service. Businesses must balance these costs to provide efficient service without incurring excessive expenses. The cost of waiting time refers to the potential loss of customer satisfaction and business revenue when customers spend too much time waiting for service. Conversely, the cost of service involves the expenses associated with providing faster service, such as hiring more staff or adding more service channels. By analyzing trade-off curves, businesses can identify the optimal point where the combined costs of waiting time and service are minimized. A basic queuing system configuration consists of three parts: the arrival process, the service process, and the queue discipline. The arrival process describes how customers arrive at the service system, often modeled using a Poisson distribution, which assumes that arrivals are random and independent. The service process outlines how customers are served, typically modeled using an exponential distribution for service times. The queue discipline refers to the rules that determine the order in which customers are served, such as first come, first served, FCFS, or priority-based service. Analyzing operating characteristics of waiting lines involves examining various performance measures, such as the average number of customers in the system, L, the average time a customer spends in the system, W, the average number of customers in the queue, LQ, and the average time a customer spends waiting in the queue, WQ. These measures help managers understand the efficiency and effectiveness of their service systems. For example, in a single-channel model with exponential service times and an infinite calling population, these performance measures can be calculated using standard queuing formulas. In a single-channel queuing system with exponential service times, the average arrival rate and the average service rate are critical parameters. The traffic intensity is defined as the ratio of the arrival rate to the service rate. When the average arrival rate is faster than the average service rate, the system becomes unstable, leading to an infinite queue. Therefore, one of the key assumptions in MM1 models, single-channel, exponential service times, infinite calling population, is that the average arrival rate must be less than the average service rate to ensure system stability. The MM1 queuing model is based on several key assumptions that define its structure and applicability. Firstly, It assumes that arrivals come from an infinite or very large population, meaning there is no practical limit to the number of potential arrivals, ensuring the arrival rate remains constant regardless of the system's state. Secondly, it assumes that arrivals are Poisson distributed, indicating that arrivals occur randomly and independently over time at a constant average rate, which is typical in many real-world situations. Lastly, the model assumes that service times follow the exponential distribution, implying that the time between services is memoryless and characterized by a constant average service rate. These assumptions collectively enable the mathematical tractability and analytical solutions of the MM1 model, making it a fundamental tool in queuing theory. In multi-channel queuing systems, multiple service channels operate in parallel, allowing multiple customers to be served simultaneously. The performance measures for multi-channel models, such as the average number of customers in the system, L, and the average waiting time, W, are more complex to calculate than single-channel models. These models are particularly useful in scenarios where high customer traffic necessitates multiple service points, such as bank teller lines or call centers. Deterministic service times from exponential service times in that the service times are fixed and predictable. Analyzing queuing systems with deterministic service times involves different mathematical models compared to those with exponential service times. For instance, in a single-channel model with deterministic service times, the performance measures can be derived using specific formulas tailored to the deterministic nature of the service process. Finite calling populations refer to situations where the number of potential customers is limited, such as a repair service for a fixed number of machines in a factory. Analyzing queuing systems with finite calling populations requires adjustments to the standard queuing formulas to account for the limited number of customers. These models are essential in understanding the dynamics of service systems with a restricted customer base and ensuring that resources are allocated efficiently. Before using exponential distributions to build queuing models, the quantitative analyst should determine if the service time data fit the exponential distribution. This step is crucial because the accuracy of the queuing model depends on the appropriateness of the underlying assumptions. If the service time data do not fit the exponential distribution, alternative models or distributions should be considered. In a multi-channel single-phase queuing system, the arrival will not pass through multiple service facilities. Instead, customers are served at one of the parallel service channels. This configuration contrasts with multi-phase systems, where customers may go through multiple stages of service, each with its own queue and service mechanism. Understanding the difference between single-phase and multi-phase systems helps in selecting the appropriate model for analyzing and optimizing service operations. Unit 9. Simulation modeling. Simulation modeling is a powerful technique used to replicate the features, appearances, and characteristics of real systems. It allows analysts to understand complex systems and predict the impact of different decisions. Simulation modeling offers several advantages. It can handle complex systems with multiple variables and interdependencies that are difficult to analyze using traditional analytical methods. It also allows for the examination of different scenarios and the impact of various decisions without disrupting the actual system. Moreover, simulation can provide insights into system behavior over time, helping managers make informed decisions. However, simulation also has its disadvantages. It can be time-consuming and expensive to develop and run simulation models. Additionally, simulation results are only as accurate as the data and assumptions used in the model. Managers must generate all the conditions and constraints for the solutions they wish to examine, which can be a challenging and meticulous process. Despite these challenges, simulation remains a valuable tool for understanding and optimizing complex systems. Monte Carlo simulation is a specific type of simulation that relies on repeated random sampling to obtain numerical results. It is particularly useful for systems with inherent uncertainty and variability. The 5 steps of Monte Carlo simulation are: 1. Define the problem. Clearly specify the system or process to be analyzed and the objectives of the simulation. 2. Determine the variables and probability distributions. Identify the key variables that affect the system and their probability distributions. 3. Construct the simulation model. Develop a mathematical or logical model of the system that incorporates the identified variables and their relationships. 4. Run the simulation. Use random sampling to generate values for the variables and run the simulation model repeatedly to obtain a range of possible outcomes. 5. Analyze the results. Evaluate the simulation outputs to make informed decisions and identify potential improvements to the system. Monte Carlo simulation can be applied to various domains. In inventory control, simulation can help determine optimal inventory levels and reorder points by modeling the variability in demand and lead times. For example, a company can use Monte Carlo simulation to model different demand scenarios and determine the best inventory policies to minimize costs and avoid stockouts. In queuing theory, simulation can analyze the performance of service systems by modeling customer arrivals, service times, and queue behavior. This approach helps managers understand the impact of different service configurations and policies on waiting times, service levels, and customer satisfaction. For instance, a bank can use simulation to evaluate different teller configurations and determine the optimal number of tellers needed to minimize customer wait times. Simulation is also valuable in machine maintenance. By modeling the failure rates and repair times of machines, simulation can help managers develop maintenance schedules that minimize downtime and maximize equipment availability. For example, a manufacturing plant can use simulation to model the maintenance needs of its machinery and determine the best maintenance policies to ensure smooth production operations. Verification and validation are critical steps in the simulation modeling process. Verification ensures that the simulation model is implemented correctly and functions as intended. It involves checking that the model's logic and calculations are accurate and consistent with the real system. Validation, on the other hand, ensures that the simulation model accurately represents the real system and produces credible results. It involves comparing the simulation outputs with real-world data to ensure that the model behaves as expected. One example of simulation modeling is analyzing the drive-through system of a coffee shop. Cars enter the drive-through to place an order, proceed to pay for the food, and then pick up the order. This system can be modeled as a multi-phase queuing system, where each phase represents a different stage of the service process. By simulating different customer arrival rates, service times, and queue configurations, the restaurant can identify the optimal setup to minimize customer wait times and maximize throughput. Another example is a trucking company with a single mechanic responsible for repairing 50 trucks. As trucks break down, the mechanic is called to make repairs. If the mechanic is busy, the trucks must wait to be repaired. This situation can be modeled as a finite population system where the number of potential customers, trucks, is limited. By simulating different failure rates and repair times, the company can develop maintenance policies that minimize downtime and ensure that the mechanic can handle the repair workload efficiently. Simulation modeling is also used in cost analysis of queuing systems. The waiting time cost can be based on either the time customers spend in the queue or the time they spend in the entire system, depending on the situation. For example, if the waiting cost is based on the time customers wait for a truck to be fixed before it can be placed back in service, the cost should be calculated based on the time in the system. By simulating different service configurations and policies, managers can determine the optimal setup to minimize waiting costs and improve service efficiency.